Hello students, today I will teach you the methods of preparation of haloalkenes. Before I start the preparations, I should recap the last classes what we have read. We have discussed about haloalkenes haloarenes and its application. We have discussed classification of haloalkane haloarenes based on number of halogens attached to the alkane system, that is monohaloalkane, dihaloalkane, trihaloalkane, tetrahaloalkane. Similarly, monohaloarene, dihaloarene, trihaloarene, and like this. And also we have discussed classification based on hybridization, that is the halogen attached to sp3 hybridized carbon called alkyl halide, benzyl halide and allyl halide. Similarly, based on sp2 hybridization, we have also classified haloalkane into vinyl halide and aryl halide. Then we have discussed the nomenclature of different haloalkenes haloarenes, and at last we have discussed question and answers. Today also we will discuss preparations of haloalkenes by different methods, and then also we will discuss question and answers. Let us start the first preparation of haloalkane, that is from hydrocarbon, or that is from alkane. How can we prepare haloalkane from alkane? Look at the slide. We can prepare from hydrocarbon or alkane by this method. How? As you know students, hydrocarbon or alkane formula CnH2n plus 2, and if you remove one hydrogen and you put one halogen, you get haloalkane. But how can you do this thing? By using some reagent. So we need reactant and we reagent to prepare product. The reagent in this case is halogen and diffused sunlight or ultraviolet light or UV light. And the mechanism which follow this reaction is free radical substitution reaction. In the product at last will be the alkane, haloalkane or Rx. The next slide you see it. The example. The example is methane when undergoes chlorination in presence of sunlight, then one hydrogen from methane replaced by one halogen, in this case it is chlorine, to prepare methyl chloride. So, methane is the reactant, Cl2 is the reagent, sunlight is the catalyst, and we are getting the product methyl chloride. How it occurs? That means we need the mechanism. Before that, you remember students that this reaction is a chain reaction, means the reaction will not stop at methyl chloride state, it will undergo further reactions in this way. Look at the slide. Once you get methyl chloride, then one more hydrogen replaced by one more chlorine atom by the similar process to get methylene dichloride or dichloromethane. Similarly, dichloromethane further reacts with chlorine in presence of sunlight, giving you trichloromethane, and trichloromethane at last undergo the same substitution reaction by replacing hydrogen by a chlorine atom to get carbon tetrachloride. So, you get not only one product methyl chloride, but you get methyl chloride, then what? Dichloromethane, then trichloromethane, at last you get tetrachloromethane, means we get mixture of products, not only one product, but we get mixture of products. This is because of the free radical substitution reaction. Let us move to the mechanism part. This is the mechanism. The mechanism of free radical substitution reaction takes place in three different ways or three different steps. One is called initiation, then propagation, and then termination. What do you mean by initiation? Means you need a free radical for the reaction to start. This is called initiation. How it takes place? Very simple. Cl2 is a molecule and both the chlorine atoms bonded by a single bond. And when you apply sunlight or when you give diffuse sunlight the bond undergoes homolytic fission or homolysis to produce 2 chlorine free radicals. Then each chlorine free radical attacks the hydrogen atom of methane, replacing the hydrogen and again preparing a new free radical, that is CH3 dot, called methyl free radical. This methyl free radical will now again attack Cl2 to form CH3Cl and one more Cl free radical. These 2 steps is called propagation. Means in propagation stage, Cl dot will abstract one hydrogen from methane, preparing you methyl free radical, and methyl free radical further reacts with more chlorine. You may ask the question, why the chlorine comes? Remember, we can say we have taken 1 mole of chlorine, means there are many molecules of chlorine are there in the reagent itself, in the reaction medium. So from next chlorine atom, chlorine molecule, it takes the chlorine free radical to prepare CH3 to get 3H3Cl and Cl dot. Similarly, CH3Cl, once you get it, and Cl dot, that Cl dot again abstract one more hydrogen from methane, means from CH3Cl, producing CH2Cl dot. You can look at the screen, it is there in the screen also. CH2Cl dot plus HCl. This reaction continues and you get the product CH2Cl2, then you get CH3Cl, and at last you get CCl4. In this way, these steps are called propagation. So propagation means the free radical Cl dot will abstract one hydrogen from the alkane part to prepare you haloalkane. Remember, this reaction will not stop till all the hydrogens replaced by all the halogen atoms. In this case, it is chlorine atoms. Look at the next slide, that is called termination. Once the reaction is over, then there will be a chance of termination. Means what? Two free radicals, CH3 dot and CH3 dot again recombine, because in the reaction system you have free radicals, CH3 dot free radicals and Cl dot free radicals. So, 2 CH3 dot may combine to give you CH3. Similarly, Cl dot again Cl dot may combine to give you Cl2, or CH3 dot plus Cl dot may give you CH3Cl. That means during termination you are getting methyl chloride, ethane and similar products like Cl2. So, hence I can say this is not a good method to prepare only one alkyl halide, because in this case you are getting a mixture of products due to subsequent halogenation by free radical mechanism. Now students, question arises, which alkane reacts faster by this free radical substitution mechanism? Remember students, reactivity of alkane is in the order 3 degree carbon, then 2 degree carbon, then 1 degree carbon. For example, 3 degree carbon means this one. Look at this one. This is called 3 degree carbon. For example, you have an alkane CH3 single bond C, then CH3, then CH3, and you have a hydrogen atom here. This carbon is called 3 degree carbon. This carbon is called 3 degree. This is 2 degree. CH3 single bond CH, single bond CH and single bond CH3. This carbon is 2 degree carbon, and similarly CH3 single bond CH, H, H, or CH3 you can say this carbon is called 1 degree carbon. Means a carbon attached to 3 carbons, it is called 3 degree. This hydrogen atom will be easily cleaved by in presence of sunlight. If you apply sunlight, this carbon hydrogen bond undergoes homolytic bond fission to get CH3 single bond C, then single bond CH3, single bond CH3 dot plus H dot. This bond will break, and this free radical, this is called a free radical, 3-degree free radical. 3-degree free radical is very stable, 3-degree free radical stable, then 2-degree free radical, then 1-degree free radical. It means if it is a 3-degree carbon, then from that carbon the abstraction of hydrogen is easier. Therefore, this molecule will react faster in presence of chlorine and sunlight. So, depending on the reactivity, you can see in the screen also the reactivity order written that the abstraction of hydrogen is in the order 3-degree hydrogen, then 2-degree hydrogen, then 1-degree hydrogen, vinyl, aryl at the last. And one more thing you see that benzyl and allyl, if molecules are there, then from that molecule the abstraction of hydrogen is easier as compared to 3-degree, 2-degree or 1-degree. We will see in the next case. Before that, remember, halogens are very reactive, but among halogens fluorine is most reactive, then chlorine, then bromine, then iodine. Iodine reacts very slowly, hence the reaction is reversible. You can see the screen, it is written methane plus I2 gives rise to CH3I plus HI, but the reaction is reversible. To check the reversibility, you have to add an oxidizing agent like HiO3 or HNO3 or HiO4, then the reaction will be now irreversible, then only you can get product methyl iodide. One more thing, students, you remember that fluorine, chlorine and bromine react with exothermic processes, means there will be evolution of heat, but iodination is very slow, it is endothermic. Let us see the next one, this one, an example of this one. I have taken propane, same thing, I have done chlorination, you get two products. Look at these two products, one is isopropyl chloride and the second one is N-propyl chloride, means the chlorine atom attached to the middle carbon is a major product, the chlorine atom attached to first carbon is the minor. Why this is so? Just I have told you. If you just look at the screen, also I can explain this one. This is the case, CH3, CH2, CH3. If you replace this hydrogen, this one, you get CH3, single bond CH dot and single bond CH3. This one is the secondary free radical, and if you replace hydrogen from this, look at this, this is your, for example, this one, then if you replace this hydrogen free radical, you get CH3, CH2, CH2 dot. This is your primary free radical, primary 1-degree free radical. As I have told you, 2-degree more stable than 1-degree, so there is a maximum chance of getting the major product as isopropyl chloride. Look at this one. This one is called allylic bromination, or sometimes called as the replacement of hydrogen from allyl carbon. Look at the model. See, this is your allyl, this is one allylic carbon, and I have just shown the compound. This is called propene compound, carbon, double bond carbon and single bond carbon. This is called propene, and you see this carbon, this is called the allylic hydrogen. These three hydrogens are called allylic hydrogen. I replace one hydrogen and put one chlorine. You see this one. This one is the product you get. This is called the allylic chloride. You see, this is allylic chloride because one hydrogen atom replaced by one chlorine atom. Look at this difference. This is the reactant, this is the product. This is the reactant, this is the product. And you see the differences. Double bond remains, but only the carbon atom to which is sp3 hybridized, from that carbon the hydrogen atom replaced by chlorine atom. This only happens at high temperature. Similar thing also, means a temperature of more than 700 Kelvin, this allylic bromination or allylic chromylation takes place, because allyl free radical is more stable than 3-degree, then 2-degree, then 1-degree. Look at this one, next one. You see the example of this one, I have replaced the hydrogen, marked it on the screen. the allylic hydrogen, that allylic hydrogen has been replaced by chlorine atom. Next one, this one. Why this is happening? Because the allylic free radicals are more stable. You see in the screen, I have given you one example of an allyl where you can replace hydrogen atom, and this, after replacing the hydrogen atom from sp3 carbon, it undergoes resonance. Therefore, if you are taking an allyl halide of type in which the two end groups are not of same, R and R dash of different carbon, then you may get two different types of allyl free radicals from which the chlorine atom will attack, and hence you get two different products. Look at the next one. This is benzyl, but when you replace the benzylic hydrogen, it undergoes resonance, but resonance is not stable. Once it goes inside, means it will disturb the ring system. So, only the halogen atom will attach to that carbon which is outside, will attach to that carbon which is outside the ring system, means benzylic carbon is having hydrogen atom replaced by the chlorine atom. So, getting only one product. So, benzyl compound gives one product, but allylic compound gives you two product at high temperature halogenation with excellent Cl2 molecules. Students, let us see the next example of an allylic compound of the type R single bond CH, double bond CH, single bond CH2 and single bond R prime. In this case, if you do the same process, that is halogenation at high temperature, then after the removal of hydrogen from the allylic position, the compound undergoes resonance. So, you get in the screen you can see there are two resonating structures for which if you attack the X dot free radical, then you get two different types of allylic substituted haloalkane, means the halo group will attach to different position, giving you two different isomeric compounds. Similarly, students, the next example you see, if you take a benzylic compound like toluene, then after the same at high temperature heating, the carbon hydrogen bond undergoes homolytic fission, giving you benzylic free radical. This benzylic free radical undergoes resonance. But remember student, if the benzylic free radical will undergo resonance, simply it will disturb the aromaticity, means the compound is no more stable due to disruption of its aromatic character. Therefore, the halogen atom will only attach to the CH2 dot carbon to prepare benzyl chloride. So, we get benzyl chloride only. Students, the last example of this allylic bromination is by using NBS called N-bromosuccinamide. So, same thing happens, N-bromosuccinamide if you use, then the allylic hydrogen is replaced by bromine atom and you get allyl bromide. Students, the second method of preparation of haloalkane is from alkene, and see the screen, I have taken one alkene, and you know in alkene the carbon-carbon double bond. The double bond, you know that once you break this double bond by adding any reagent like HX called hydrogen halide, then to one carbon of the double bond H will attach, the next carbon attached to the halogen, giving you alkyl halide. For example, next one you see this, I have taken an example of ethylene CH2 double bond CH2 and added HCl, and you see that the hydrogen atom attached to one carbon and the chlorine atom attached to other carbon. Remember, in this case we are using a solvent carbon tetrachloride. But students, if the alkene is symmetrical, then this is the case, means where you add H, where you add Cl, no problem, you get alkyl chloride. But if the alkene is unsymmetrical, then the addition follows Markovnikov's rule. See the next, this is an unsymmetrical alkene called propene CH3 single bond CH double bond CH2 and added HCl to it in presence of carbon tetrachloride. Look at the compound, the carbon atom to which least number of hydrogens are there, that carbon attached to the chlorine atom. Means Markovnikov's rule says that when you add one reagent like HX, then the negative part will attach to that carbon which contains least number of hydrogen atoms. Why this is so? The mechanism behind is this one called the electrophilic addition reaction. So, students, remember that when ionized it gives you H plus and Cl minus, and when propene reacts with H plus it gives you two carbocations. One is 1 degree carbocation and a secondary carbocation called 2 degree carbocation. From that 1 degree and 2 degree carbocation, 2 degree carbocation is more stable. As you know from your first year knowledge, the stability of carbocation is 3 degree, then 2 degree, then 1 degree. Depending on the stability of carbocation, 2 degree carbocation will attach to the halogen atom and to get the product isopropyl chloride. Look at this one. This is the example and I have shown you how it takes place. But remember students, sometimes what will happen that if you take an example of like this, what in the screen you can see, when you add Hx in this case, then sometimes there will be hydride shift to get more stable carbocation. For example, you are getting 1 degree carbocation, by hydride shift you can get 2 degree carbocation. If you have 2 degree carbocation, by hydride shift you can get 3 degree carbocation. If there is a possibility of stability shifting from 2 degree to 3 degree, 1 degree to 2 degree, you shift the hydrogen or you shift the methyl, any group to get more stable carbocation, and to that more stable carbocation the halide ion or X minus ion will attach. Next slide you see, this is the anti-Markovnikov's rule. That is, if you are adding HBr, remember when you are adding Hx, in case of Markovnikov's rule, X may be chlorine, bromine or iodine, but in case of anti-Markovnikov's rule, your X will be only bromine. It is because here we are taking a peroxide called organic peroxide. In this case I have taken benzoyl peroxide. In presence of peroxide, HBr bond will break to prepare a free radical, but the HCl, HF, these bonds are very strong, the peroxide cannot break these bonds. Similarly, Hi, in case of Markovnikov's rule you can add, but in case of anti-Markovnikov's rule you cannot take Hi, because Hi undergoes a very easy cleavage to give you H plus dot and I dot, but the I dot will recombine with one more I dot to give you I2 molecule. So, the free radical is not stable in that case. But in this case of anti-Markovnikov's rule, remember student that you see between carbon and carbon where there is double bond and to which carbon more number of hydrogens have been attached, to that carbon you attach bromine to get the product. This is called anti-Markovnikov's rule. In this case the example is CH3 CH double bond CH2, I have added HBr to get CH3 CH2 CH2 Br. Students, when you add halogen to alkene, for example, in this case I have taken bromine to an alkene in presence of carbon tetrachloride, the addition also follows a carbocation intermediate, but in this case a cyclic carbocation is formed and the bromine attached to each carbon. This type of compound is called vicinal dibromide. So, when you add alkene to bromine, it gives you vicinal dibromide and there is a change in color. The brown color of bromine decolorizes. This is also called a test of unsaturation, means any alkane, alkene or alkyne, how can you differentiate them, that which one is saturated and which one is unsaturated? By this bromine addition reaction by change of color. This is the addition of halogen to alkene to prepare dihaloalkane called vicinal dihalides. Look at this one. This is the thing you see in the screen, that there is a change in color. If you take alkene, then bromine water if you add, it becomes colorless after addition, but if you take alkane, the color will not change, means the color is taking the color of the bromine. See this one, this is the mechanism behind it. When you add alkene to bromine, then you get a cyclic bromonium ion, and then bromide free radical will attach to this bromonium ion and the cyclic cleavage take place to give you dibromo compound of alkane or called 1,2 dibromoethane, and the bromine, two bromines will attach to opposite, means you get trans product. Students, now we will discuss some question and answers. Look at the first question. The first question is an aromatic ring system in which the NO2 group is attached, and to that at the para position you see the ethyl group is there. So, when you do bromination in presence of ultraviolet light, as I have told you earlier that the bromination is an allylic bromination or benzylic bromination. So, the allylic carbon or the benzylic carbon, as you see in the answer written, it is surrounded by a mark hydrogen. You can see this hydrogen atom is replaced by the bromine atom. So, remember, the hydrogen atom attached to benzene ring will not remove, but the hydrogen attached to the allylic carbon or benzylic carbon will be removed, and at that carbon you attach the bromine atom. Next example, see this cyclohexene compound and we are adding bromine in presence of heat or sunlight. So, when you are adding in presence of heat or sunlight, the type of reaction is allylic bromination or benzylic bromination. You see in this case the allylic carbon, I have also marked it, which was the allylic carbon. That allylic carbon will be replaced by your bromine atom to get 1, 2, 3. It is 3 bromo cyclohexene. So, you get 3 bromo cyclohexene. Remember, if the question comes that you add bromine in presence of CCl4, then it is called addition reaction. You simply remove the double bond and put 1 bromine to each carbon bonded to carbon-carbon double bond. But in this case, as sunlight is there or heat is there, then it is called allylic bromination. Next question you see. Here you see that alkene is there. This is called isobutylene. You see the answer. I have added Hi molecule, and it is a Markovnikov's addition, because you see that the marked carbon atom is least substituted. So, I have told you earlier that as per the Markovnikov's rule is concerned, the carbon atom to which least hydrogens are there, to that carbon you attach the negative part of the compound, that is I minus in case of this Hi. So, I minus will attach to the carbon which contains least number of hydrogens, or it is called more substituted. So, you get the compound tertiary butyl iodide. This is called Markovnikov's addition. So, students, today we have discussed the preparation of haloalkanes from alkane by free radical substitution reaction. We have also discussed the preparation of haloalkane from allylic and benzylic compounds. We have also discussed preparation of haloalkane from alkene by addition of HX according to Markovnikov's rule and anti-Markovnikov's rule. Also, we have discussed question and answers based on this. Today, we will discuss methods of preparation of haloalkane part 4. That is, on part 3, we have discussed how you prepare haloalkane from alkane by free radical substitution reaction. Also, how can you prepare haloalkane from allylic or benzylic compounds by using heat or NBS, N-bromosuccinamide. Also, we have discussed how can you prepare haloalkane from alkene, from symmetrical alkene, from unsymmetrical alkene by Markovnikov's rule, by anti-Markovnikov's rule, and also we have discussed preparation of vicinal dihalide from alkene by addition of halogen. Now, we will discuss how you prepare haloalkane from alcohol, from Finkelstein reaction, from Schwarz reaction, and from Hunsdiecker reaction. Let us start one by one. That is from alcohol. From alcohol, you can prepare haloalkane by removing OH group and by introducing halogen. How it is possible? It is possible by different methods. You see it. One by using HX, or by using phosphorus halide like PX3, PX5, and by using thionyl chloride SOCl2. One by one discuss. First one from HX. Remember students that the reactivity order of HX is in the order Hi is more reactive than HBr, then HCl, then Hi. It is also same as the reactivity order of the acidity of halogen acids. Remember, similarly, there are different types of alcohols: allyl alcohol, benzyl alcohol, tertiary alcohol, secondary alcohol, primary alcohol. So, remember the reactivity order is alkyl, first is benzyl or allyl, then you have tertiary alcohol, then secondary alcohol, then primary alcohol. You can see in the screen also 3 degree alcohol, 2 degree alcohol, 1 degree alcohol. But remember students, that to remove OH group from alcohol is not so easy, because OH group is not a good leaving group. Then how can we remove OH? I will discuss in its mechanism part. Let us see the next slide, how we are preparing it. By HCl, when you add HCl to a primary alcohol or to a secondary alcohol, you need a catalyst, that is anhydrous zinc chloride. Without the catalyst, the reaction is very slow or may not occur at all. Therefore, you need a catalyst. For tertiary alcohol, due to its very high reactivity, you should not use zinc chloride. Directly you can put HCl, you get the alkyl chloride or tertiary chloride. The first two methods, that is preparation of from primary and secondary alcohol using anhydrous zinc chloride and hydrochloric acid, is called Grove's process. The product is alkyl chloride. Look at this next slide. This is the mechanism how the reaction takes place. I have told you the removal of OH group is not so easy. So, use zinc chloride. Zinc chloride, zinc 2 plus ion coordinates with oxygen atom, forming an intermediate, that is O plus ZnCl2 minus. This one is a very good leaving group, and now from the carbon chain, that is from CH3CH2, this leaving group departs and the chlorine atom attacks to the carbon atom, and you get the compound CH3CH2Cl. The mechanism behind the the Grove's process, or by using zinc chloride, anhydrous zinc chloride method. Next one, students, you see this one. This is by using HBr. You can use HBr or you can use KBr H2SO4, you can use NABr H2SO4, no problem. Same thing happens. The OH group removes, bromine comes in, and you get bromoalkane. So, ROH plus HBr, you get RBr, and you also get the byproducts. If you are using KBr, the byproduct is KHSO4 and water. Remember, students, what I have told you earlier, that the removal of OH group is not so easy. Then how to prepare or how to get the remove this OH group? This is by using this type of acids. What is that? The mechanism says that the OH lone pair takes the H plus ion from HBr, forming you OH2 plus. Remember, OH2 plus is a very good leaving group. So, OH2 plus means water easily removes, forming a carbocation, and to that carbocation, the next slide you see the carbocation is formed. That to that carbocation, the bromide ion attacks to give you tertiary butyl bromide. Means in the step 1, we have seen that the OH lone pair attacks the hydrogen atom of HBr, forming OH2 plus, and then OH2 plus is removed to form a carbocation, and to that carbocation, a stable carbocation, 3-degree carbocation, Br minus attacks to get you the product. See the next slide. By using HI, here also you can use Ki, but for Ki you should use the acid H3PO4 called phosphoric acid. Same thing, you get byproducts, the removal of iodine and the removal of OH group and the incoming of the I. You get Ri plus, along with you get the byproduct like water, or in case of Ki you get KH2PO4 and water. But the methods is similar thing. We are removing water. You can see OH and H, I make a box of it, that you should remember that water is coming out and the two group I or any halogen and R, they will attach to give you haloalkane. Look at this. I have taken one alcohol. In this case, the alcohol, the carbon atom to which the OH group is attached is a secondary carbon. To left of it, the carbon is a tertiary carbon. So, if you have an alcohol where secondary carbon OH group is attached, and to the left of it you have a tertiary carbon, there is a chance of hydride shift. I have told in the earlier class also. Why hydride shift? OH group, if attached to H plus ion, it gives you unstable OH2 plus, it is a good leaving group. Once the OH2 group removes, then it gives you a carbocation. It is a secondary carbocation, and by hydride shift you can get a tertiary carbocation. Remember, tertiary carbocation more stable than secondary carbocation. So, once you get tertiary carbocation by hydride shift, then the chloride ion or any halide ion will attack to that carbon to give you the resulting product. Remember, this type of shift equal 1 to hydride shift, because the carbocation is at one position and the hydride means the hydrogen atom is at the next carbon, that is a 2 position. So, shifting is from 1 to 2 called 1 to hydride shift. This is because for the formation of more stable carbocation. Similar thing you can see in the next one, 1 to methyl shift. Same example I have taken, only I have just put one more alkyl group at the carbon, at the adjacent carbon, means the tertiary carbon. You see the carbon atom is 4 degree carbon, because you have 3 methyls attached to that carbon. The methyl group, you can see it is red color, methyl group shifted to the next carbon by hydride shift. Why this is? Because that carbon is more stable, means after shifting of the methyl group, the carbon becomes tertiary. The tertiary carbon is more stable, hence it is called that 1 to methyl shift, because methyl group shifted from 1 to 2 position. It is forming a more stable carbocation, and a more stable carbocation will give you the product. Next one, see the next method by using px3 or px5. Remember students, px3 means PCl3, PBr3. Sometimes you may also use red phosphorus and halogen, red phosphorus and chlorine, red phosphorus and bromine. But remember, bromine and iodine, you see that px3, X may be bromine, chlorine or iodine, but normally when we are reacting with PCl5, when you react and PCl3, they react differently. When you use PCl3, the reaction will be 3ROH plus PCl3 gives rise to 3RCl plus H3PO3. You simply for balancing, you put 3ROH. Remember it. When you are using PCl3, you use 3 alcohol to get 3RCl. But when you are using PCl5, no problem. ROH plus PCl5 gives you RCl is the product. Along the byproducts are POCl3 and HCl. Well, let us see the mechanism behind the addition of PBr3 to alcohol. Remember again, I have told you the OH group removal is very difficult. So, you have to make a good leaving group. Therefore, we are using PBr3 or PCl5 or PCl3. What is there? You get a trialkoxyphosphine or RO3P when you add PBr3 using 3 alcohol. This trialkoxyphosphine, you see the next slide, this trialkoxyphosphine now when reacts with HBr, then phosphorus takes up the hydrogen, forming you a very good leaving group. See, good leaving group is required to remove the OH from the R group and to introduce the halogen. So, once the good leaving group is formed, means oxygen and phosphorus bond, you can see that the good leaving group is there. Then the bromide ion attacks in this way. The alkyl group and the next part, that is the phosphorus oxygen part, removed, because phosphorus oxygen bond is very stable. So, they form P double bond O and the compound becomes RBr. So, students, when we are using PBr3 or PBr5 or PCl3, remember that we are reacting with alcohol to remove the OH group, and this is because we are getting an intermediate good leaving group, that is phosphorus oxygen bond, which is a good leaving group, hence we are getting the product easily RBr. Next one, you see we can prepare also haloalkane from thionyl chloride called Dargen's procedure. In this case, you are using SOCl2. The mechanism also there, you can see the step 1, step 2, same thing. To remove this OH group, when you are adding SOCl2, oxygen forms a bond with sulfur. When oxygen forms a bond with sulfur, you get an intermediate ROS, Cl and Cl. This is the intermediate, very good leaving group, means we are preparing a good leaving group to remove the OH group. Next one, you see it. Once you get the good leaving group, then the reaction takes place by SN2 mechanism. I think you know it. SN2 mechanism means the halide atom or halide ion will attack the R, the substrate, and immediately the leaving group departs. Means the attack of the reagent Cl minus and the leaving group they take simultaneously. You see here in the screen, Cl minus attacks the carbon, the R group, and the leaving group departs, forming you RCl along with SO2. This is the best method till now what I have discussed, because the byproduct is SO2 is a gas, and hydrochloric acid is also gas, or if you are using any solvent, then it is in the solvated form. So, the preparation of alkyl halide is in purest form, or Darden's method is used to prepare a very pure alkyl chloride. So, students, till now what we have discussed? We have discussed the preparation of haloalkane from alcohol by using what? The hydrogen halide method, HX method, then by using what? By PX5 or PX3 method, and also by using what? Using the thionyl chloride method. So, from these three, the thionyl chloride is the best one to prepare. Remember students, that one important thing you always remember, that the removal of OH group, and again I can say you that the reactivity order is 3 degree more reactive, then 2 degree, then 1 degree. Okay. So, 3 degree, 2 degree, 1 degree alcohol is the reactivity order. Now, we will discuss some problems based on the things I have taught you now, the preparation part. Okay, now see this problem. This is one compound, you can see on the screen that you have a cyclohexyl ring system, and above which you have OH group, and below you have methyl, and above the arrow it is SOCl2, means a compound is given and you want to react with SOCl2. Just I have told you few minutes before, this is called Darden's method of preparation of haloalkane. When you use SOCl2, the OH group is replaced and Cl groups comes in. See the answer, OH group replaced and Cl comes in, along with this you are getting SO2 and HCl. That means, this is a problem comes from Darden's method by using thionyl chloride, replacement of OH group and introduction of Cl to get the product, and product is there on the screen. Next question, question number 2. You see that there is an alcohol called benzene ring system, 2 OH groups are there. So, in 2 OH groups, one OH group is outside the ring, one is attached to ring. So, when you use ZnCl to HCl, the OH group which is outside the ring system, that is called that CH2OH group, that OH group will remove and Cl will attach, but the OH group attached to ring will not remove, because due to resonance it forms a partial double bond, or the OH group attached to ring directly will not remove, but the OH group which is outside will be removed by using HCl and ZnCl2, and this OH group replaces and the Cl comes in, and the product is there on the screen. Okay, students, now next preparation is from Finkelstein reaction. It is also called halogen exchange reaction. Why? Because the reactant we have taken is Rx, and X is chlorine atom or bromine atom, means we are taking chloroalkane or bromoalkane. So, from one haloalkane we are going to prepare another haloalkane called alkyl iodide by this Finkelstein method. As we are exchanging halogen, hence it is called halogen exchange method. See the reaction, Rx plus NaI, NaI is the reagent and acetone is the solvent used here to get Ri plus NaX, which is chlorine or bromine. Take an example, if it is methyl chloride or methyl bromide and you have added NaI, sodium iodide and acetone, you get methyl iodide and respective sodium chloride or sodium bromide. This reaction we call Finkelstein reaction, conversion from chloroalkane or bromoalkane into iodoalkane. Next one is the Schwarz reaction. This is also important because we are going to prepare fluoroalkane. As you know, from alkane to get fluoroalkane is very difficult due to the reactivity of fluorine is very high and the reaction is extremely exothermic. Therefore, you can prepare by an alternative method, that is from alkyl halide. It is chloroalkane or bromoalkane, you can get fluoroalkane. Here we are using the reagent silver fluoride, cobalt fluoride or antimony fluoride, anyone you can use. Here I have used silver fluoride. Hence, the reaction is Rx plus AgF gives rise to Rf plus Agx. Agx is a precipitate, you can easily separate it and you can get fluoroalkane. So, Schwarz method is used when you are converting bromoalkane or chloroalkane into fluoroalkane. This is called the Schwarz reaction. Let us see the next one, Hunsdicker or called Bododine-Hunsdicker reaction. Students, this method is best to prepare alkyl bromide. Here the reactant is silver salt of carboxylic acid or RCOOH. In the screen you can see the formula RCOOH called silver salt of carboxylic acid or silver alkanoate. When this one is treated with the reagent bromine and heated, means heat is the catalyst here. Without heat, the reaction will not take place because the mechanism says that it is a free radical mechanism. That means the bromide free radical, bromine free radical is going to be substituted. So, now in this case you see the product RBr, CO2 and AgBr. This method is very good because the byproducts are, one is in precipitated form or you can say that one is in terms of a precipitate and the other one is a gas, carbon dioxide. See the example, if I will replace HR by methyl, it is called silver acetate plus bromine heated to get methyl bromide, carbon dioxide and silver bromide. And now the product is CH3Br, means you have only one carbon. So, if in the conversion question will come to convert one compound into another by decreasing a carbon chain, then this method is used to decrease to do the things. This is called Hunsdicker reaction. Let us discuss its mechanism. This is the mechanism. The mechanism passes through a free radical reaction and you see that when RCOOAg treated with Br, it gives you RCOOBr plus AgBr. This RCOBr on heating gives you two radical. One is RCOO dot and other one is bromide radical Br dot. RCOO dot is unstable. You further heat, then you get R dot plus carbon dioxide. R dot means alkyl free radical. So, this alkyl free radical is unstable. It further reacts with bromine molecule and displaces bromine by simple homolytic cleavage, means bromine-bromine bond will break by homolytic cleavage to give you bromine free radical, and this bromine free radical now attacks or now attached to the alkyl free radical, giving you alkyl bromide and a new bromine free radical. So, this is the step called propagation. So, in initiation we are preparing a free radical RCOO dot and Br dot, and the propagation step we are preparing a new free radical R dot, which takes one bromine radical from bromine molecule and producing the product RBr and Br dot. Next, see the termination step. As you know, when there is a free radical reaction, three steps: initiation, propagation and termination. In termination means when the reaction is going to end. At that time also the free radicals recombine, just like here you see bromide Br dot combines with one more Br dot giving to Br2 molecule, or R dot combines with R dot to give you RR molecule. RR means alkane. So, you see that I have told you in the last slide that this method is used to convert a compound having higher carbon atoms or number of carbons if n, then you can get compound haloalkane having n minus 1 carbon, but the one thing drawback is that here you are getting RR, means alkane. That means you are not getting RBr, also getting RR or alkane. So, it is not so suitable method, but best method for bromide, but here we get the byproduct alkane RR. Students, so we have discussed all the methods of preparation. Now, we will go to discuss one or two problems. Look at this. So, we will discuss the problems one by one, only one or two problems I will discuss. That is how to convert this compound isopropyl alcohol into N-propyl bromide. Very simple, you can do by different way, but the shortest way you should write it. Anyway, I am writing it how to convert this compound. Very simple. First of all, you use concentrated sulfuric acid. Concentrated sulfuric acid. This is a dehydrating agent. Dehydrating agent. So, this one what we will do? It will simple remove this water molecule from the isopropyl alcohol, giving rise to this compound. This is called propene. This is called now propene. Propene by dehydration, removal of water. Then you add HBr. Then you add HBr and you add a peroxide. This is called anti-Markovnikov's rule. AMR, anti-Markovnikov's rule. Addition of HBr to peroxide, then you get this compound. One more example, very simple one. Look at this molecule. This is benzene attached to one iodine and then attached to CH2I. You are going to simply replace this iodine by fluorine atom. For example, this is chlorine, let it be chlorine like this. You are going to replace this chlorine to add fluorine. How do it? You use AgF and heat it. Then what you will do? Remember, you get this one. The chlorine atom attached to CH2 group is going to be replaced, but not this chlorine, because this chlorine undergoes resonance with the benzene ring system like this. So, this chlorine is not going to be removed due to its conjugation of the benzene ring system. So, when you use Schwarz reaction, you cannot remove this chlorine, but you can only remove this chlorine, but this is a free chlorine atom outside the benzene ring system. So, students, in this class I have discussed you how can you prepare haloalkanes from alkane, from alkenes. Also in the previous class we have discussed it, and today's class also we have discussed how to prepare from alcohols and from Schwarz reaction, from Finkelstein reactions and from Hunziker reactions. Also we have discussed question and answer relating to it. Therefore, students, you go and practice problems whatever I have taught you. Definitely if you have listened it carefully and if you do your homework, you can able to question all the answers of the question what it is there in your mind. Therefore, today I am ending this class. Thanks to all of you.